All right, we're gonna wrap up here. Last little bit of two. We'll roll through three. We'll roll out of here, hopefully. So obviously last time in chapter 2 there, we were talking mainly about the idea of how really want you to show your work in chemistry and the idea of conversions and dimensional analysis. Once again, from any type of equality, like 1 foot is our 12 inches, 5,280 feet is 1 mile. We can write two conversion factors from that, a foot over 12 inches, or 12 inches over 1 foot. Remember that the proper way they want you to show work here in chemistry as you continue through your journey and in this class is to show the conversion factors and dimensional analysis, which is setting it up so that you could clearly see the units cancel. So again, if we had 45 inches and we wanted to go, say, 2 miles or something like that, maybe we would do our opposites cancel. So we're basically multiplying and dividing when we do dimensional analysis. So we would put the 12 inches on the bottom, the 1 foot up on top. Inches divided by inches will essentially cancel each other out. If we want to go one more step, the importance of setting it up like this, as we talked about, is you can clearly see that the feet are up on top. So really all I have to think about is opposites to get rid of it. So if we wanted to get to miles, we would put the feet on the bottom and the mile up on top, and the feet would cancel. Once again, we would multiply whatever is on top and come back through, as we talked about, and divide by whatever's on the bottom. The other thing that we talked about is as we do these type of problems or calculations in general, we do want to make sure that we end up with the right number of significant figures in our answer. And that is based on, especially when we're doing something like this, sort of dimensional analysis as well, is based on the least number of significant figures, as we're only multiplying and dividing in this type of calculation. There are certain conversion factors that are considered, as we talked about, exact numbers, which means that they do have as many significant figures as you like. And the importance of that in calculations is, again, we do not even sort of consider those when we're doing a calculation. And remember that if it is a straight English to English conversion, that's going to be considered an exact number. If it's a straight metric to metric conversion, that also would be considered an exact number. Really, if you're using some type of equality, the place where you do have to sort of think about that conversion is if you cross over from metric to English. Outside of those couple or so that we talked about, like 1 inch is exactly 2.54 centimeters, that's still considered exact. And they want you to use 453.6 grams as 1 pound is also an exact conversion. But any of those other ones where we go metric to English, like I think we looked at the milliliters to quarts sort of conversion, you should look at it. And remember that when you do look at it in that sort of sense, you are looking at the one that is the number part of that conversion, not the one that is 1. So there's usually 1 for one of the numbers and usually a number for the other. And you want to look at the actual number when you're doing that. So in this particular case, this would be considered exact. That would be considered exact. And really the only one that we would really want to reference in this case would be that initial sort of value there, which would have 2 significant figures. And if we math here, whatever we got there, we would go to 2 significant figures, which again, we also talked about rounding, not going crazy with that. And you may have to do a scientific notation type of deal. The other place where you might have to look at a conversion in terms of their significant figures is like in a couple of examples I think we did last time, that in the actual problem, they sort of give you a conversion factor to use. Then you typically should look at sort of the significant figures in those numbers when you're doing a calculation. We finish up real quickly on density, which is where we're going to pick up on. Density is mass divided by volume. And the density of an object, as we talked about there, a substance will sink or float, for example, and things that are more dense than water will sink, and things less dense than water, for example, will float. Any questions on any of that stuff we talked about last time? All right, so let's pick up our conversation here with density. I think we saw this slide. The other important thing about the density is the density of water. And density of liquid water, again, in any type of book problem that you may come across or need to use the value for water, usually 1 gram per milliliter is the value that you should use. And that's another one of those figures that you do need to know, just sort of know. As we talked about, density does change with temperature. So technically speaking, if the temperature is really not like 20 degrees or 25 degrees, the density really won't be 1. But pretty much 99% of the time, if you find yourself in a problem that you're doing and you somehow need to incorporate the density of liquid water, that 1 gram per milliliter is definitely the value that you should use. Density has a formula which is mass divided by volume, and it has certain units. And most of the time, the units of density are grams per milliliter, are grams per cubic centimeter, which is typically what we use for solids and liquids. We don't deal too much with it in this particular class, but in the next class that you take, usually the density example are given in grams per liters, the typical density units that you associate with gases. For us in here, probably grams per milliliter, grams per cubic centimeter is definitely in the 2 units that you will see. The number always stays with the grams part, and it's always like 1 milliliter, 1 cubic centimeter sort of on the bottom. Also a reminder, right, a milliliter is basically a 1-to-1 conversion between that and a cubic centimeter. Obviously, those are 2 different ways to get volumes. We can take the volume by simply just reading the volume, or we could do something like you did last week by taking some length measurements of like the square or the wood block, the length times the width times the height, which will give you your volume in cubic centimeters when you cube that. We also need to know how to properly rearrange this, right? So density is mass divided by volume. We times the volume to each side and divide by the density. Volume is mass divided by density. Our mass is volume times density. Sometimes people like to remember everybody's favorite place, the DMV, right? Triangle. So density is mass over volume. Volume is mass over density. And mass is density times volume. It's just a quick way to remember it. We will, in a lot of cases, has to be, or you will be able to sort of solve for any of those sort of variables there: volume, density, or mass. Any questions on that there? All right, so let's take a look at an example here. So let's grab a calculator and we'll knock this one out here. A block has a volume of 25.3 cubic centimeters. It has a mass of 21.7 grams. What is the density of that block? Okay, so since obviously we're dealing with density, that would be a good place to start. We have a volume given to us of 25.3 cubic centimeters. We do have the mass, which is 21.7 grams. So clearly, if we just kind of check off what we got, density seems like a pretty good thing to solve for. We're ready to put it just directly in here. So 21.7 grams divided by 25.3 cubic centimeters. When we divide it out here, we'll end up with 0.858. The units are grams per cubic centimeter. Once again, the number goes with the grams part. The cubic centimeter is basically 1, and they don't cancel out, obviously, in this case. In terms of significant figures, I got 3 there, right? It got me 3 there, so I probably should have 3 significant figures there as well. Yeah. Any questions on that one there? So as I mentioned, there's really kind of a few different ways that you can get a volume. And as I mentioned, just simply if you're doing a liquid, you can fill it up in a graduated cylinder, read the meniscus, and take the reading. If you're doing some type of solid like that block that you did, you could use a ruler and do some measurements. The third very common way to get the volume of an object is also like what you did last. Well, under some water and you threw a stopper in there and you read it before and after that you did it. And that's volume by displacement. Volume by displacement means that if you put a solid object into something like water or liquid, it will basically just is equal to its own volume. So before she takes a dive in here, we have a certain initial volume of water in the tank. She dives, feet first, hopefully. And when she does, obviously the volume in that tank is going to rise to sort of a final volume. And if we take the difference in the water level, and if I could draw straight lines, that difference between where it started and where it did end, that would basically be the volume of the object, or her volume in this particular example. And that's a very common way to find a volume of a solid object. This is just simply send it for a swim in some water, take an initial reading before you do that, take a final reading after you do that. And again, the difference in the volume will give you the volume of that particular object. Hopefully, again, those are stairs, not just markings, so she could crawl out, or she could hold her breath for a long time. We'll hope for the best. We'll see her next semester and see how she did. All right. Well, hopefully you won't see her next semester. I'll see her next semester. Let's take a look at this one here. A filtered cylinder, 25 milliliters of liquid. She then drops a solid in it. It goes to 33.9 milliliters. The solid has a mass of 63.5. What is the density here? So take a few minutes, see what you come up. Yeah, let's take a look. So again, this is sort of what we were just describing. We got basically a terribly drawn graduated cylinder here that's starting with 25 milliliters of water in it. We're going to take that solid that has a mass of 63.5 grams, and we're going to drop it in. When it does so, once again, we should see the volume level there rise to our final volume here of 33.9 milliliters with our solid in there. It's our initial volume. So the first thing that we really want to think about is the volume here, so that we can go into our density equation. We do have the mass good to go right now. So our volume would be our final volume minus our initial volume. And that's going to give us 33.9 milliliters minus 25 milliliters. Going to give us 8.9 milliliters, I believe. Now we have the volume. We can actually calculate the density of our object by taking 63.5 grams divided by 8.9 milliliters. And that is going to give us 7.1 grams per milliliter as our final answer here. Any questions on the calculation? I ended with two significant figures because of why? It really does go back to this, right? We are subtracting, which means we actually should be looking at decimal places. That's 1 decimal place, 1 decimal place, which means our answer should go to 1 decimal place. But that answer with 1 decimal place still has two significant figures, right? Which is important because the last thing that we did was divide, which means we should now look at significant figures. And this has 3 significant figures. This has 2 significant figures. That means my answers should end up with 2 significant figures. Any questions about there? All right, so here again is density of some common object. As I mentioned before there, liquid water actually is 1 gram per milliliter, which is a common value that you use. I think we talked about it last time, but again, water is an unusual substance in the fact that its solid version is actually less dense than its liquid version, as we might have talked about. And that again is because when water molecules come together in the solid state, they actually can't get very close to one another, and it creates a lot of open volume between the different water molecules. So once again, if we just think about that density equation, because in ice we have a much greater volume than we would say in a liquid state where they could actually get closer to each other and not so spread out. We actually end up with a smaller volume for ice than it is for liquid water. And that's an unusual characteristic of a substance. Most of the time, it is the solid version that is more dense than the liquid version as well. So everything here is going to sink in water, right? Everything here is going to float in water. Here's some other density values as well. By the way, if I take a Diet Coke can and a regular Coke can, and I put it into a sink of water or a big body of water, what will happen to those? Will they sink? Will they float? Well, the answer is one will do this. And one will do this. Yeah. One will sink and one will float. Which one will sink? It's a good party trick, by the way. It is Coke. Yeah. Because Coke has what in it? A lot of sugar. Yeah. Makes it more dense. So the regular Coke will sink. The Diet Coke has artificial sweetener, right? Not as dense. And it actually will float. Like I said, good party trick, just in case you need a trick to do. That does happen. All right, so let's take a look at one last example here. A student needs 150 cubic centimeters of salt for an experiment. The density of salt is 2.16 grams per cubic centimeter. How many 1 pound boxes of salt do they need to buy? This is one of those conversions you do need to know. 1 pound is exactly 453.6 grams. All right, take a moment or two, see what you come up with here. Okay, let's take a look. So obviously we're dealing with density, mass, so divided by volume. We do have a volume, which is what the 150 cubic centimeters is. We also have the density given to us, which is 2.16 grams per cubic centimeter. Now you can use density like a conversion factor and sort of do some problems with dimensional analysis, which means you could, if you needed to, flip the density around and kind of use the centimeters cube up on top and the grams on the bottom if you had to do, some type of dimensional analysis sort of approach to this. If you're not sure where you should start, you have density given to you, you have volume given to you. I'm just going to go out on a limb and say mass seems like a good thing to maybe solve for in this case. We're going to multiply the volume to the other side, going to give us volume times density. I'm actually going to do more of a dimensional analysis sort of calculation here. We would take our 150 cubic centimeters, which is our volume. Once again, we'd just go opposite, so you don't even have to worry about, by the way, rearranging this correctly if you take a more dimensional analysis approach, because all you have to remember is opposites cancel, right? So I'm just going to put my opposites in the right location. And now this should remind you of what you should be doing, which is multiplying. So dimensional analysis can be very helpful in the sense of you might not even have to kind of rearrange an equation per se. You just got to think about what units you got to get rid of and what you got to end with, and it'll help you kind of do the math part correctly. So we're going to do that and end up with 150 times 2.16. Going to get you 324 grams, as the cubic centimeters would cancel. In this case, if I were going to put an answer here for grams, that is 3 significant figures, right? That is 2 significant figures, as that 0 is not significant because there's no decimal, which means if we were going to give sort of an answer here in terms of how many grams we needed, it would be in like 320 grams in this particular case. We also want to make sure, though, that we do answer the actual question that's being asked, which is the question is how many 1-pound boxes do they need to buy, which means you should have plenty with 1 box, right? So this brings up a couple of important points. Make sure you do answer the question that's actually being asked, right? Which is, in this case, how many boxes should you buy? 1 box will do. You'll have some left over. And again, we still want to keep track of our sort of significant figures along the way. Any questions on any of that there? Comment. So that should wrap up chapter 2, I believe. We're going to go off then to chapter 3. Okay, we're off to chapter 3, which is about matter state, which we kind of covered a little bit earlier. We'll also talk about physical and chemical changes and mixtures, which is relatable to obviously the lab. We'll be doing it about an hour or so. So let us get into this. As we talked about previously, I think, but just officially here, matter is basically the stuff that the universe is composed of. It has space. We talked about pretty much it's anything that you could kind of touch, see, and feel, I guess. There's 3 states of matter, as we talked about. There is our solid state, which once again, in the solid state, everybody is usually packed in there pretty tight to one another. They're not really moving past each other. They just kind of walk into place, if you will. They have a definite shape, and they're difficult to change because they are rigid. and they're rigid because you got everybody just piled in together right on top of each other. So it creates a pretty solid surface, if you want to think about it that way. And that's why things are very hard to change that are solid. The other state of matter, right, is our liquid state of matter, where once again, things are still relatively close to one another, but they actually do have, again, energy to sort of pass one another. And as we talked about, that is why liquids are thought to be fluid and they pour. Liquids, now, on the other hand, do not have a definite shape, but they will take the shape of whatever container you have, but they do have a definite volume. So basically what that means is if you had 10 milliliters, say, of water, and I took that water and put it in a water bottle, it would take the shape of the water bottle. If I poured it into the trash can over there, it would take the shape of the trash can. If I put it in one of those silly straws, right, to go all circles, it would take the shape of that. It should still be 10 milliliters of water no matter what container I put it in, as long as I'm not a klutz and spill it. I should still have the same volume no matter sort of which container that it is in. And obviously the last state of matter is gas, and that is the state of matter where everybody, again, has basically broken apart. And again, when we get to the gas chapter, as they're flying around, there are collisions that are occurring. And it is these collisions that associate pressure with gases, or that we associate pressure with. Gases, on the other hand, basically takes the container it's in, and it fills uniformly as it's flying around. One of the things we'll learn about when we get to the gas chapter is the idea of an ideal gas. You maybe have heard about it. And one of the things that makes it an ideal gas is the idea that the volume of the gas molecule itself is not really important versus the volume of the containers flying around in. So we oftentimes look at the volume of the container for a gas as the volume of the gas present. I think we also talked about some of the transitions as we go from these states. And again, just a reminder that as we go from solid to liquid, that again is the process of melting. As we go back from liquid to solid, that is the process of freezing. Liquid to gas is evaporation or vaporization. Gas going back to the liquid is condensation. We could also go from solid directly to gas, skipping the liquid, which is our sublimation. And we could go from gas back to solid, also skipping the liquid cleanup, which is deposition. So these, again, are changes of state, as we talked about, and the importance of energy with that is sort of change, really important. So again, as we go from solid to liquid to gas, those are all processes where energy needs to be absorbed or put in. And that is what is known as endothermic. So again, I think we might have talked about the ice cube. We put heat picking up from the surroundings, going to start to melt, take the liquid water and put some fire underneath it. It will continue to evaporate at its boiling point where that will occur, right? This is the normal melting and boiling point. I'm sorry, melting and freezing point. And that happens at the same temperature, like 0 degrees Celsius for water, as we talked about, I think. And also that is the normal boiling point over there, which is 100 degrees Celsius for water at that point. Opposite is true as we go from gas to liquid to solid. Energy is released. And again, that is exothermic, basically, what that represents. So that is also, again, why when we get into the solid state, it has released a lot of energy, or most of its energy. And that's why everybody sort of locks into place, because they no longer have enough energy to basically move past each other. It's also, again, why in the liquid state, they have a little bit more energy. So they're able to sort of move past one another, and our liquids are more fluid. And state, they have a lot of energy, right? Otherwise, they wouldn't be flying around, and they have enough energy basically to escape one another and fly around. Any questions on that there? Yeah. There's some liquid in different containers there. Here's some pictures, speaking of water, as we talked about, and again, the unusual characteristic of water. And it has a lot to do with how water molecules interact with each other, and how one molecule interacts with another. and that could be a different molecule, it could be the same molecule, how they interact with each other. That is what is known as intermolecular forces. And basically, intermolecular forces is how molecules basically interact with other. And basic interaction of intermolecular forces is essentially opposites attract. So in chemistry, opposites attract, much like in life, right? They always say that, right? Opposites attract. Two people that are very positive don't want to be around each other, too cheerful. Two people that are negatively don't want to be near each other. So somebody with like a positive attitude, negative attitude sort of balances each other out, right? And the same thing happens here. Things with opposite charges are attracted to each other, and things with the same charge, like positive charge and positive charge, or negative charge and negative charge, want to get it away from each other as far as possible. They're repelled by each other. So how molecules interact is actually between that electrostatic attraction, which is the positive and negative attraction between molecules. And when we look at something like water, and we'll learn this as we go through some different chapters, water is what's referred to as being a polar molecule. And that basically means that there's a side to water that's more negative, and it's actually the oxygen side. And the hydrogen side is actually more positive in water. And when two water molecules get together, the negative side of one is attracted to the positive side of another. And that, in this case, is what's referred to as hydrogen bonding, which is a very strong sort of intermolecular force. And it's that strong force that when they do come together with that lack of energy as they're coming into the solid state, as you can see here, creates all this open volume between the different water molecules. And that's, as we talked about, what kind of bloats the volume in terms of its density, and why the density of ice is actually less than liquid water. This is actually water in its liquid state, and actually because it possesses a little bit more energy, they're actually able to get themselves closer to one another than when they get in that solid state and they're lacking a lot of that energy. They really do sort of spread out and creating that big open volume. So again, that's a very unusual characteristic of a substance, as I mentioned. Most of the time that solid is going to be more dense than liquid, but this is basically the reason why that is. As I mentioned before, as well, the intermolecular forces, like we were just talking about, like the force that holds, say, a water molecule together with another water molecule, is also a really important factor in things like boiling points, melting points, freezing points. The stronger the attractive force between two molecules that are the same, you're going to have higher melting points and boiling points, because it's going to take a lot more energy to try to pry them apart from each other, because they're going to be held together really tightly. And that translates into a higher temperature, as opposed to something that if you have two molecules that are held together by a super weak force, you just look at it and it will just kind of break apart. And those are things that are sometimes referred to as being volatile. You maybe heard that word. Volatile is like liquids, for example, that if you just look at it, it will jump into the gas phase really, really easily. It's also why certain molecules are in the liquid or gas phase versus the liquid stage under normal conditions. Things like methane, like when you light your Bunsen burner, is a gas. Yeah, propane, butane, those are all gases that you could easily ignite and set a fire with, right? But they're all in the gas phase because they're really what are referred to as, we'll talk about, non-polar molecules, and they're held together by super weak forces. Like you just look at it and they're just ready to go into the gas phase. And a lot of organic molecules, for example, if you go to organic chemistry, they throw you in a fume hood to do your work, because a lot of organic molecules are held together by that really weak force, which means even if you're using a liquid, it could go into the gas phase really easily. And a lot of them are flammable, right? And as you know from activity one, we should use no flame, right? With anything that's flammable. Yeah, even a small flame is enough to set it on fire. And that's why they oftentimes work inside a fume hood to keep all those fumes from going through the room and perhaps getting set on fire when you don't want to. So this is a table from your book that describes solid, liquid, and gas like we talked about. But really, those sort of intermolecular forces are really important to determine whether or not, perhaps something would be a solid, a liquid, or a gas. Again, the stronger those forces that hold it together, most likely is going to be more of a solid or a liquid. The weaker the force is going to be more of a gas. So let's talk a little bit about physical changes, chemical changes, and things are. Let's first talk about physical properties. Physical properties can be measured by observing some changes in the substance that you're looking at. Some typical physical properties are a physical property, and physical properties really do sort of go with the idea of a physical change. And the important part about a physical change is basically this: what we start with and what we end with are really fundamentally the same thing. So fundamentally, nothing has really changed. So when it goes physical change, what you with and what you end with is really still the same thing. So for example, we could take our water as a pretty good example of that. If I have an ice cube, which is a solid version of water, right? It is still H2O fundamentally. I take that ice cube and I let it melt. It's now liquid water, which is still H2O, just in a different sort of state. And if I take liquid water and I want to cook some pasta and I start boiling some water, I'm going to turn that liquid water into steam, right? Which is basically still H2O. So although it may appear different, it is still the same fundamental thing. Still three of those phases, and that is just a physical change. It has not changed to anything different. So typical physical properties are things like odor, color, volume. The state, as I just mentioned, liquid to gas are super common physical changes that you do. Density, melting points, and boiling points, again, are also physical type of properties and also physical changes. So physical changes a lot of times involves a lot of physical sort of properties to do something, like you want to boil something, you want to freeze something, you want to melt something. So those are all a lot of times will result in a physical change that occurs. So the important part, again, physical change, what you start with, what you end with, exactly fundamentally the same thing. If I had a peanut, right, and I cracked it, it is still a peanut, just in a lot of small pieces, right? It is fundamentally still the same thing. Nothing has changed. It may just have a different appearance when you look at it, but it is still really fundamentally the same thing. The other thing is typically a lot of times in a physical change, you could actually kind of get back the original thing by some type of physical means. Like the example of the water, you could put it back in the freezer, get the ice cube, right? You could like take it out of the freezer, it'll melt to water. If you had a lot of patience, you could glue back your, pieces of peanut and you'll have your whole peanut sort of back together as well. Now, that is different than a chemical property, which is usually associated with a chemical change. And a chemical change is basically what you start with in this case and what you end with are different things, are fundamentally different things. So what is a chemical property of a substance? A lot of people look at a chemical property as that substance ability to go through a chemical change, basically a chemical reaction, or even its ability to resist a chemical change or a chemical reaction is sort of a chemical property of it. Most chemical changes are referred to as chemical reactions. Some type of reaction has occurred and you make new things. So for example, if you took something like some iron and a little bit of oxygen and perhaps a little bit of moisture, you will make rust, yeah, which is the iron and the oxygen now chemically united. They started out as separate things, but have joined here to make. You could take something like rust and do a lot of physical things to it, heat it, cool it, boil it. I'm not sure why you want to do all that, but freeze it, whatever it may be. But you'll never get back the iron metal by itself like it originally was, and you'll never get the oxygen gas back. So you can't get it back by any type of physical means. Same thing if you took some hydrogen gas, perhaps, and a little bit of oxygen gas, make a little bit of H2O. I'll balance it like I know chemistry. There we go. We got something going on just like that. hydrogen gas, oxygen gas makes water. And like we just talked about, you could heat it, you could boil it, whatever you want to do, you could freeze it. You're still going to have water at that point. It will not give you back the hydrogen or oxygen gas through any type of physical means. You could definitely do a chemical reaction, which I think we'll do later on, or you'll do later on in a lab. You could run an electrical current over the water, for example, and break it back down into hydrogen gas and oxygen gas. But that would be another chemical change that will essentially happen in that case. So you could, if you wanted to, do this move and run an electrical current over it. And it will break it back into hydrogen gas and oxygen gas. But again, that is another type of chemical reaction that's occurring. That's what's referred to action when you decompose something into its kind of parts. So chemical change involves what you start with and what you end with, something turning into something fundamentally different than what you started with. You can't do any type of physical process to get back that original substance, and that is the difference there between a chemical and a physical means. Obviously, making a hard-boiled egg is going to change the egg chemically as it gets heated up. And as we eat food as well, right? When we eat food, we break down our food, right, in our stomach, and we use all that stuff for all kinds of processes through our body. You can't get that food back in the original form it was in. And it has definitely been altered, obviously, and through a chemical change. So the importance here is a physical change involves, again, one or more physical properties, but again, no change in that fundamental component. Most common, as I said, is really our changes of state going from solid to liquid to gas and backwards. Chemical definitely involves something new being formed as a result of that. Hypothetically, if you took some zinc and you reacted with some hydrochloric acid, perhaps the zinc would come in here and kick out the hydrogen and make some hydrogen gas, and a little zinc chloride action happening there. Hypothetically, like in an hour or so, maybe when you do it. This is a chemical change that's occurring. You had zinc metal, which is just a piece of metal by itself. You had hydrochloric acid, which is a solution. It will make hydrogen gas, which are bubbles that you will see, and you'll be left with another solution, which is really zinc chloride in this case. And again, a definition of a chemical change has occurred, and that's definitely a chemical reaction that has occurred. So chemical changes, again, are reactions. The tarnishing of silver, for example, any metal that goes through oxidation is a chemical change, because really what oxidation is of metals like rust and stuff like that is actually a redox reaction is occurring. Electrons are being transferred, and that is an example of a chemical change occurring. It's also can change certain properties, doing things like that. For example, maybe you're familiar with if you coat metals with certain other metals, it can protect the metals that are underneath it. It changes some properties of that metal and maybe will make it less resistant to going through oxidation as well. Question on physical changes, chemical changes. So let's talk a little bit about elements and compounds. An element is really, if you want to think about it on the periodic table, as far back as you could go. That is basically your general representation of everything. The general way that an element is represented is as an atom. And we'll talk about that in another chapter. But atoms have protons, which are positively charged, electrons, which are negatively charged, and some have neutrons, which have no charge. So basically, all elements are represented by atoms, and depending on how many protons you have, will give you different elements. You could think of elements as really like the alphabet, right? There's like 26 letters, I think, still. But many different combinations of those letters gives you a lot of different words that you could have. And it's sort of the same idea here with different combinations of elements, different numbers of some elements. You could form what are referred to as compounds. And compounds is the combination of two or more atoms from two or more different elements. So for something to become a compound, which can be made up of two or more elements, you do need that important. And compounds, and another word that people sometimes have trouble with sort of figuring out the difference, is molecules. And molecules is really just, you could think of it like a general definition of a combination of two or more atoms. So what is the difference between these two? It is this part of it. In order for something to be a molecule, you simply just need to get, I got two or more atoms. Could be two or more atoms of the same, could be two or more atoms of different elements. You simply just need two or more atoms for it to be considered a molecule. A compound, on the other hand, you need two or more elements involved for it to be a compound. So to further confuse some things is certain elements, for example, from the periodic table, and by the way, if you pull an element off, like example, so just so you know, nothing has charges until they come together, like metals and nonmetals come together. If you just have a piece of zinc by itself, it really has no charge or anything from the periodic table. But there are certain elements, the way that they come is they come as twos, basically. So hydrogen, for example, oxygen, nitrogen, chlorine, fluorine, bromine, and iodine. These all come as twos, which are really referred to as being a diatomic, di meaning two, atomic meaning atoms, molecules. So hydrogen, the way it naturally comes is it comes as like two hydrogens bound together, sharing some electrons. Oxygen, the way it naturally comes is two oxygens sharing a few electrons there. And that is how it naturally comes. So each of those things, and by the way, most other elements up there are what are referred to as being monoatomic, which means they come as ones, basically, one atom. Hydrogen, oxygen, nitrogen, chlorine, bromine, fluorine, and iodine. These are all molecules because they come as two atoms basically together. They're also all elements because the only element involved in hydrogen is two hydrogens. The only element involved in oxygen gas is two oxygen. There's no other element involved. Is hydrogen, oxygen, nitrogen, chlorine, fluorine, bromine, and iodine, are they considered compounds? They're not considered compounds because they don't have another element involved. It's just the same one. Now, if we took something like water, like we talked about previously, water is a molecule because there definitely is two or more atoms involved. It is also a compound because it involves oxygen and hydrogen that is present, and is water an element? Water is not an element because it has hydrogen and oxygen, two different elements together. So sometimes people get confused as like, is this a molecule? Is this a compound? So the best way to think about it is, like I said, a molecule is just kind of like a basic definition, and all you have to reach is there two or more atoms? It doesn't matter if they're the same or different. In order for it to be a compound, you got to have two or more atoms, and you need to have two or more elements sort of involved. Any questions on any of those there? So as we talked about there, you can obviously take something like water, as I mentioned before, run that electrical current through it, and break it apart into hydrogen gas and oxygen gas. And you could take it from its compounds to its elements, right? But once you get here to its elements, again, that is as far back as you could go. You cannot break those guys down any further. So we could definitely do chemical changes or chemical reactions where we take a compound and break it off into its elements. That is, again, sometimes referred to as like a decomposition reaction when we do that. Also, some properties of elements versus their compounds are usually very, very different. water has a very different property than hydrogen gas and oxygen gas that make it up. And that is very good because hydrogen gas and oxygen gas is actually not so great explosive, right? So very, very different. Same thing with, for example, we had sodium and chlorine. Got a piece of sodium metal. It's like a really soft metal. You could cut it with like a butter knife. And if you had chlorine, it's like a toxic green gas. But through the miracle of chemistry, right, we get sodium chloride, maybe some salt. We put it on our fries. We're happy, right? Maybe in that scene. But you wouldn't want to put like chlorine gas on your fries or anything like that. Not good recommendation. So usually the compound, when things come together, have very different properties than the actual elements that make them up. So a compound, like I said before, is that substance that always united in the same proportions. So if we do have water, no matter where you get your water, you should always have 2 hydrogens for every 1 oxygen that's present. May just cost you more depending on how it's bottled, but it should still fundamentally be H2O no matter what it is. It should also have like that law of conservation of mass, right? It always has 2 hydrogens and 1 oxygen. It should always have a mass of like 18 grams. It should always have like 2 grams of hydrogen for every 16 grams of oxygen, or 1 gram of hydrogen for every 8 grams of oxygen, no matter where you find it, if it is water, in terms of that relationship. As I mentioned just a second ago, we definitely can take those compounds through some type of chemical change, chemical means, to break them back down to elements. And again, that is as far as we could go. And compounds, again, always contain different elements, and like CO2, which is this, and that is carbon and oxygen together. And again, that would be a compound. That would also be a molecule of CO2. And once again, that would not be a element of CO2. Any questions on compounds, molecules, elements? So the next thing we're going to talk about then is mixtures and pure substances. So a pure substance is pretty much what the name implies. It is basically you just have one substance present. No other substance is there. So for example, if you had just pure water, you would just have water. If you had just pure ammonia, you would have ammonia. Sugar, you could also have a pure substance as an element, like if you just had gold, or you had a whole bottle of zinc, like you'll see later, or copper. It's just that element by itself, then it is a pure substance. Pure substances usually have pretty distinct characteristic properties that allows you to identify one pure substance from another. Clearly, water and ammonia have a very different smell. Ammonia is like kind of like Windex, smells pretty strong. Water, obviously, hopefully doesn't have any type of smell to it. Also, gold, right, obviously would look very different than, say, water and stuff like that, or sugar. You go try to pawn some sugar and say it's gold, it's probably not going to work because they don't look anything alike or anything like that. So they usually have very true characteristics that allow you to identify them. When we take 2 or more pure substances and actually put them together, we get what is known as a mixture. So for example, if I take my friend water, that is a pure substance. And if I take, my friend salt, or some sodium chloride, for example, that is also a pure substance. And if I throw them together, my salt will actually dissolve in my water, and I will actually make something like a sodium chloride solution, or basically salt water, right? And this is a mixture. Now, the important part of a mixture is this. When you do a mixture and you put together these 2 substances or more substances together, they actually still retain their identity. So even though they're in a mixture, they actually still retain their identity. They don't change. So right off of that description, when I make a mixture, is that a physical change or a chemical change? It is a physical change. So nothing changes. They keep who they are, even though they're mixed together. So that is your definition of what you start with, and what you end with is still the same thing. A mixture, as we'll talk about, you could get back any part of the mixture just like they originally started by doing some type of physical means. So when we make a mixture, that is what is referred to as a physical change. And when we make something like sodium chloride, I put that little aqueous symbol next to it. This guy right here. That's the aqueous symbol. That means that it is a water environment. And basically, that is what is referred to really as a solution. So when you make a solution, all those reagents you use in the lab that are basically liquid and drops that you do, those are solutions, those are mixtures. That's a physical type change that occurs. You could have something like this where the mixture looks the same. You could also have a mixture, say if I take, like you're going to do today, sand and some water, right? If I take a mixture of sand and water, I could take that sand and put it in there and mix it for as long as I want. It will never dissolve. A mixture of two pure substances of water and sand together. And that one is a little bit easier to see the identity of each of them. You could actually physically kind of see both parts of the mixture in that case. And that brings us to the different types of mixtures that we have. Bless you. A homogeneous mixture, which is also sometimes called a solution. In a homogeneous, sufficient mixture will look the same throughout. So the salt water example, right? If you take salt and you put it in there, it will dissolve in the water. And if you just looked at it, it will just look like water. Like if you grab some water out of the ocean and nothing else is floating in the ocean, and you just get the water, it looks just like water. But if you taste it or have been in the ocean and you tasted some of that water, it tastes quite salty, right? And there's salt dissolved in there. Those are homogeneous mixtures. So you mix it, everything mixes really well. Everything looks the same throughout. It looks like one phase, sometimes it's referred to, one layer. It just all looks the same. And that is definitely what's referred to as a homogeneous. Same thing if we took some sugar and water, we would expect the sugar to dissolve. Once again, it will just look like water to you if you look at it. But if you taste it, you would probably taste the sugar that's in there. The other type of mixture is a heterogeneous mixture. And in a heterogeneous mixture, it's kind of like our sand and water mixture. You can mix, like I said, that sand all day and it's never going to dissolve. And in a heterogeneous mixture, when you look at it, you can see different layers. You can see the different parts of it. Like today, you're going to do that. You're going to take some sand, some salt, and some water. When you put them all together, the salt should dissolve, which will give you a homogeneous mixture of the salt and water. But the salt, water, and the sand now makes a heterogeneous mixture, right? Because you'll be able to see the sand in it. And in a heterogeneous mixture, you'll still see those layers. Best example, obviously, of a heterogeneous mixture is like chocolate chip cookies, right? You see the chocolate chips, right, in those cookies, right? So it looks good. You mix it, but you still see the different layers that are in there. Obviously, if you took some sand and some metal pieces in there, right, you can stir all day, mix all day. Nobody's going to dissolve in each other. You'll still be able to see those things. So homogeneous, everything really kind of mixes really well. Looks like the same throughout. Heterogeneous, you definitely see individual components, different layers that are there. As I mentioned before, it doesn't really matter the type of mixture you're dealing with. The homogeneous mixture, the heterogeneous mixture, you can separate it out by some type of physical means and actually get back both components or all the components of your mixture, which is essentially what you're going to do today in the first lab, is basically to use physical means to separate out all the components of your mixture. So how can you do that? Well, there's a few different processes that we could use to allow us to separate out mixtures. So let's just take one process, which is one you'll do today as well. And that's the process where if we have some type of solid and a liquid, that's a really good way to separate it out. So let's just take our sand plus your salt water, for example. So once again, that sand and salt water together, the salt water and the sand is a heterogeneous mixture. Again, we would see the sand in it. And if we take a filter and filter it, so basically take a nicely badly drawn film, that's not too bad, funnel. You're going to put a filter paper up there. And like a good chemistry student, you also put something underneath to catch what's coming through. So if I take my sand and saltwater mixture and I throw it in here, which is definitely our heterogeneous mixture, right? The water part, right? The saltwater part should drip through, right? Now caught up here on the filter, it's going to be your sand, right? And now through this physical property or physical change here, really our physical method, I guess is what I'm trying to say there. Through this physical method, we're able to separate out our sand, which we could open up our filter paper, let it dry out, and it'll be like good old sand that's dry. We obviously will have the saltwater part as well. So we've now separated both components of the saltwater and sand mixture by physical means. We're able to do this separation because we're actually taking advantage of physical properties. On a piece of filter paper, you can't see it, but there's holes. And it only allows certain size of stuff to go through, like water and salt that's dissolved in water. And it's able to go through. And doesn't allow bigger things like sand are too big to actually go through, so it actually gets caught. So we're using like a physical property of like size to sort of separate these things out in this particular case. Any questions on that there? So while we're here halfway through your lab, the second part is you're going to grab this up, right? And we're going to take like your salt water, which this guy at this point is a homogeneous mixture. And remember, in a homogeneous mixture like salt water, you can't really see both parts, right? It just looks like water. So we can definitely separate this out through another process that takes advantage of kind of physical properties. But before we do that, let's talk about really what's happening with the salt water before we actually talk about what we're going to do to it. So when we have something like salt water, like a sodium chloride solution, the sodium and the chloride here are actually ions in this case. It's a sodium ion, which is positively charged, and there's a chloride ion that is negatively charged. And when it starts out as a solid, before you dump some water on it, that is basically what is there. And those guys are attracted to each other really strongly. And you see it as a solid when you like take the salt shaker, or later today when you grab the sodium chloride beaker there that has it in it. What happens when we dump water on it, which again is a polar molecule, has a negative side and a positive side, is we dump so much water on it that it is able to actually pull these guys apart from one another. And how it dissolves is like the positive ion is going to actually be attracted to the negative side of water, which is the oxygen side. So all these water molecules basically will start surrounding the positive ion. And the good thing about water is it also has a positive side, which means the negative ion is going to find itself surrounded by water, but it's actually going to be surrounded by the hydrogen side of water, which is the positive side. Remember, opposites attract. So we're going to have water surrounding here. Now, very commonly when people think about making a solution like this or taking something like dissolving salt in water, is this a physical change or a chemical change? It is a physical change. So a solution is a homogeneous mixture, right? And a mixture is a physical change. This is a physical change, even though we can't see the sodium chloride anymore when we dissolve it. We can't see it because there is a crap load of water molecules everywhere, right? So it's no longer visible to us. They're actually still there. And because there's so much water molecules there, it keeps the ions apart from each other so they can't come back and make the solid like it originally was. We help the process of dissolving because we pour water on it, and then what do we usually do? Mix it, right? So that's adding energy, right? It's also throwing a bunch of water all over the solid, right? So that's going to allow a lot of water molecules to get on that solid and start separating them out from each other. And then it eventually will dissolve to a point where there's just too much water molecules for us to visually see this sodium chloride anymore. Still there, right? It is actually still there. So that's actually what is your salt water, what's actually in your saltwater part of it. So we could take advantage of the differences actually in the two components of this mixture, which is the water part and actually the ion part or the ionic part of it or the salt part of it. And we could do a process horribly drawn, but we'll see a much better picture in just a second. I know I failed art 3 times, but I think it was the effort. I passed stick figures. Stick figures, I was good, but regular art, not so good. So we take this apparatus and we throw our salt water, which is basically what we were just talking about there. And it's sort of a closed environment. It has like a receiving flask over here. This tube that connects it is usually kept really, really cold. So this tube that kind of connects both parts is kept really, really cold. And we put our salt water in that side, and we take our Bunsen burner, also known as an arrow, pointing upwards, and we start to heat the salt water. What's going to happen? Yeah, so if we go back to really what the salt water is, right? As I start heating that salt water, I'm going to start plucking off all these water molecules, right? And they're going to go off and now become steam, right? So we're going to get all this steam from the water part that's going to happen. Steam's got nowhere to go but down the pathway of least resistance, which means when my steam, which is in the gas phase, hits something that's really cold, what type of process is it going to go through? It is going to go back to liquid. It's going to go through the process of condensation, right? Going from gas back to liquid. And what will happen on this side is we will get our water dripping out on the other side. We will continue to heat this until essentially we have driven off all the water molecules. So once we drive off all the water molecules that originally had all of our salt dissolved, that means that there's going to be nothing between these two guys other than, cool, I can see you again. I want to now definitely hook back up with you. That's a super strong attraction. That's what's known as an intramolecular force. That's like one of the strongest attractions you can have, a positive and negative ion coming together. And they're going to just come back together. And what you're going to end up with on the left-hand side here is you will end up with no more water, just the salt is going to be left over there as you're heating it. And through this process here, which is known as distillation, we'll do my salt right here. We have now got our salt back, which once again, we could let dry out and just be not obviously wet with water anymore. And we have our water. We got both parts of this homogeneous mixture back in its original form, even though we couldn't at any point when it was in the mixture form see the salt, right? We couldn't see it at all, but it was still there. And this is an illustration that it is a physical change that's happening here, because definitely it changed to anything else. And very common people think some type of chemical reaction had to happen because I don't see it anymore. It's gone, right? And in this case, we really didn't do anything other than make a solution. You will actually do this, except that you won't use this nice apparatus because they don't want you to break it and it costs a lot of money. So you're going to use an evaporating dish, basically, yeah, and you're going to throw your salt water up there, and you're just going to heat it on your ring stand with your Bunsen burner. We are not going to collect the water in this case. The water is just going to be lost as steam right out into the air. But eventually, as you continue to heat it, what will be left in your evaporating dish will be your sodium chloride in the first experiment and your zinc chloride in the second experiment. At that point, you're going to do kind of the same thing on the second experiment. You take that zinc chloride solution after you get rid of the hydrogen gas, and you're going to heat it up. It's going to release the water part of it, which is why it says in the instructions, take the water solution and pour it into your evaporating dish. It's really not water, but it's zinc chloride surrounded by water, and you're going to heat off the water in that case, and you'll be left with the zinc chloride that will come back. So what we're really doing in both of these cases through filtration and distillation, which is what this is we're actually taking advantage of these things' physical properties to allow us to separate them. In the case of something like sodium chloride you could heat the crap out and it will never go into the gas phase. So you could heat it as much as you want and it won't go into the gas at all. Water, you just need to hit 100 degrees and you got into the gas phase, and you can do that easily. So using the differences in their physical properties and that difference in boiling point, which is a physical property, we're able to separate out both the water in this case from the salt water. And again, you're doing the same thing in your evaporating dish. You're just not collecting it. So what I just drew there is distillation, and filtration is obviously with the funnel and the filter paper. Here's I don't know, I guess you could say a better picture of it, but that's maybe what it looks like in a real life situation. And again, you have your salt water here. You're heating it with your Bunsen burner, very cold tube, out comes your water, and eventually you'll be left with your salt that is left over. Any questions on that? Here again, just a summary of what we talked about. Matter can be homogeneous mixtures or heterogeneous mixtures, which can be separated out by physical means to get back to pure substances. Remember, pure substances can either be elements or compounds, and you could take compounds back to elements, and that again is as far as you could go. I think they call that chapter 3. Yes. Any questions on that? All right.